All right, welcome to lecture, and we'll get started in a minute or two. We're picking up with the next chapter-ish stuff. Again, this handout should be up online. In case you haven't seen it, it should still be there. So let's give everybody a minute or so before we get going. And like always, again, if you have any questions throughout the lecture, make sure you do type them into the box, and obviously I will answer them at some point. Even if I had moved on from that slide, like I said, I'll go back and make sure I answer them. So last time we did finish the last chapter, which I think was officially chapter 5, I think. So we're going to kind of talk about really in this chapter, stoichiometry, concentration, molarity. We're going to talk about some different types of stoichiometry. So that's why I think it kind of pulls from a variety of different sort of chapters. It's kind of a potpourri of where all this stoichiometry type stuff is in these chapters. All right. So since we last chapter, actually, maybe it was 7. It was 5. I think we talked about types of reactions. So we talked about balancing equations. We also talked about ways you could classify reactions, and there's many different ways, including basically 2 sort of big classifications: the double displacement reactions, which sort of underneath those reactions you had precipitation reactions. You also had acid-base reactions. You had some gas generating reactions as well that fall sort of under that double displacement window. You also had sort of redox reactions, which a lot of other reactions sort of fall underneath those as well. Things like synthesis reactions, where we take 2 things to make one thing, decomposition reactions, where we take one thing and break it apart into a couple of things, single replacement reactions, where one element comes in basically and replaces another in a compound. Those are, again, also really redox reactions. More of your classic not really classic, but more general definition of combustion reaction, which again is not necessarily the organic combustion reaction, but the one that involved really just having O2 present. Those also are basically redox reactions. Again, redox meaning oxidation reduction reactions. Oxidation meaning you lost electrons, reduction meaning that you gained electrons, and those things always happen together. So as one loses, one gains the same number of electrons along the way. And then in lab, we lectured on how to balance more complicated redox reactions. So again, if you were not there, you should probably go watch that video. Again, it's going to help you a lot with experiment 9, which is the redox of iron. It will also help you a lot with the study assignment if you're not sure how to kind of balance those things. And I think that's study assignment F, which is redox reactions. So we talked about kind of how to go through those and balance them in acidic and basic conditions. And we actually, I think, did a couple directly from the lab as well. So there's a couple of things, the way that sort of study assignment is written, that you need to sort of be aware of. So again, make sure you do go watch that so that you will know how to actually do it. All right, so what we're going to do now in this chapter is sort of put a couple of things together. We're going to put our grams to moles sort of calculation together, along with balancing equations. And we're going to talk about stoichiometry, which is essentially using balanced equations to figure out, for example, how much product you may make. You can also figure out, if you know how much product that you did make, how much reactants you started with. So stoichiometry and sort of basic stoichiometry problems allow you to figure out a lot of sort of things. And really all you need to sort of figure those things out is typically the balanced equation and basically one piece of information about a reactant, about a product. And that one piece of information is something that will allow you to figure out the moles of it. And really, stoichiometry is based off of the idea of a balanced equation. And when we have a balanced equation, let's say we have H2 plus O2 gives us H2O, put a 2 there, maybe a 2 there. So when we look at a balanced equation, essentially, we could look at these coefficients that we see in the balanced equation as the moles of each of those guys. So those can represent the moles, which again is MOL, not molecules, but moles. And we could come up with several relationships. For example, we could say for every 2 moles of H2 that we throw in there, we also need to throw in there 1 mole of O2. We could also say that for every 2 moles of H2 that we put in there, we should get 2 moles of H2O out. And again, none of this is any type of calculation. It is strictly just the coefficients from the balanced equation. We could also say that for every 1 mole of O2 we put in there, fix that there. Try that again. So again, for every 1 mole of O2, we get out 2 moles of H2O. These are all what are known as being stoichiometrically equal with each other. They are clearly not equal with each other based on numbers. So clearly 2 does not equal 1, but they are equal to each other in terms of like proportion. So for this reaction to sort of take place properly, for every 2 moles of H2 that you put in there, you should throw in there also 1 mole of O2, and you can do that with each of them. It's kind of like when you make cookies, right? In order to make cookies, you need to put so much flour, so much chocolate chips. You need the right proportion of everything in order to say bake a dozen cookies. It's sort of what stoichiometry is. It's sort of you need the right ratios of each of these guys for this reaction to properly take place and for you to, for example, produce enough product. Now, because ultimately these are all really equalities, right? An equality is 2 things that are essentially equal to each other, but maybe on some different scales. We technically could, for each of these guys, write 2 conversion factors. So for the guy on the right here, we could say that for every 1 mole of O2, we would have 2 moles of H2O on the bottom. Or we could write the opposite conversion factor, 2 moles of H2O, tongue-tied there, 1 mole of O2. For this equality here, we could write for every 2 moles of H2, we get 2 moles of H2O. We could also say for every 2 moles of H2O, you get 2 moles of H2. And lastly, for this sort of top equality here, we could say there are 2 moles of H2 for every 1 mole of O2. Or we can say for 1 mole of O2 on top, there is 2 moles of H2 on the bottom. So really from this one individual sort of equation, we're able to come up with essentially 6 different conversion factors. And sometimes people freak out about stoichiometry, like what is it and all that good stuff. But really what stoichiometry, really is is really just a conversion factor. And instead of like going to a table to find your conversion factor, you will find your conversion factor from the balanced equation. And this is why when we do stoichiometry problems, having a balanced equations is super important, because obviously if your equation is not balanced, then you will have none of the right proportions in terms of mole to mole relationships, and everything will be wrong. So really all of this starts with a balanced equation, and really stoichiometry is nothing more than a conversion factor. And it's usually because in a lot of problems, they will give you a piece of information about one thing in the problem, but you're actually interested in somebody else in the equation or the reaction. So you need a way to go from one thing in the balanced equation to another in the balanced equation. And pretty much like most conversion factors, you definitely will not use all 6 of them in a problem. It would just be based on, obviously, the particular problem. So for example, let's say I had 32 moles of water that was produced, and I wanted to know how many moles of O2 did I start with. So when we do stoichiometry, as we'll talk about in just a second, usually the first thing that you want to do is take whatever they give you and convert it into moles, which in this case, it already is since I started with moles. And then what you want to do is look at what they gave you, which in this case is moles of water, but we're really not interested in water. We're interested in O2. So this is really where the stoichiometry comes into play. We need to find a relationship between water from the balanced equation and O2 from the balanced equation. And that's really the conversion factor that's going to allow us to go from water, which we're not interested in this problem, to O2, which we are interested in. And those conversion factors, which we already wrote over here, would be one of these 2 conversion factors. So if we were going to do this problem, we would start with 32 moles of water and basically treat it like a conversion in dimensional analysis. Water's on top, so we want to get rid of it. So the conversion factor that will help us do that is the one on the left there. 1 mole of O2 will go on the top. 2 moles of water will go on the bottom. This is the big stoichiometry moment. The moles of water will cancel each other out. So we're essentially taking 32 and dividing it by 2. And that's going to give us 16 moles of O2. That technically would be, based on this equation, if we produce 32 moles of water in this production, we would have had to throw in there 16 moles of O2. Now, a lot of times we're not necessarily interested in moles. We're interested in a more usable type unit. And a more usable type unit usually is grams. So a lot of times in stoichiometry, we do a lot of conversions of going grams to moles and moles back to grams. So these are 2 really common sort of stoichiometry conversions that we do. And I hope at this point you know how to do that, but just a friendly reminder, it is the molar mass from the periodic table, right? So it's the molar mass from the periodic table that will help us go from grams to moles if we need to. Or in this particular case, if we wanted to take those moles of O2 and convert them into grams, we would use the molar mass, where the moles of O2 would be on the bottom. The grams of O2 would be up there on top, which would be 32 grams. The moles of O2 would cancel each other out, and we would take 16 times 32, gets us something like 512 grams of O2. If you want to get specific, probably significant figure wise, 510 grams would be the right answer, but we won't look at that at this moment. And that's a basic sort of stoichiometry sort of process. Again, you will use the balanced equation to figure out the mole to mole relationship. Sometimes an additional step is at the beginning. You have, for example, grams of water here, and you may have to use again the molar mass of water from the periodic table, for example, to get you to moles. So these are the basic sort of stoichiometry sort of steps. You do want to sort of treat stoichiometry really like a conversion factor. Although I did get answers at every step, you could also do it all in one ginormous step when you do it. And when you deal with basic stoichiometry problems, as we'll see in just a second, there's really 4 basic steps that you follow. And if something is done for you, then you just go on to the next step. You don't go backwards or anything like that. But really, most stoichiometry problems, especially sort of basic stoichiometry problems, they're really just the 4 sort of steps repeated over. Any questions on how to get the conversion factors, the stoichiometric relationships from the balanced equation? Again, there's really no math in terms of that aspect of it. It is just the coefficients from the balanced equation. While we're talking about sort of molar mass on the back end here, remember as well, when you calculate molar mass, the units are grams per mole, which means this should always be 1 mole. So for some reason, people, when they do like O2, or perhaps if O2 had a number in front of it in the balanced equation, people always want to, when they do the molar mass, take this number into account. And you shouldn't do that when you're doing molar mass. It should always be simply just straight from the formula, from the periodic table. And again, that gives you how many grams there would be per 1 mole. Again, the 2 that would come in front that I put an X through, this 2 right here, if you needed to use it, it would be used in the stoichiometry part of the calculation. You don't want to do it in the stoichiometry part of the calculation and then in the molar mass part, because you're just going to get the wrong answer because you did it that way. So that's a common mistake that a lot of people will make, is they'll try to incorporate the coefficient in the balanced equation into the molar mass. So molar mass is strictly just take the formula by itself, add up all the parts, and that gives you the grams per mole. All right, so let's take a look at these 4 sort of steps, are important steps when we are doing a stoichiometry problem. And essentially, the first one is really the most important. Nothing will be good in any calculation that you do if you are not starting with a balanced equation. So if you're given everything in words, you want to make sure you first convert those words into the correct formulas. You then want to make sure that you balance the equation with the coefficients. If you're given the actual equation and you see numbers in it, it's probably a pretty good chance that it is going to be balanced. If you're given a chemical equation and you actually don't see any numbers in it, I probably would take a moment and double check that it is balanced. So you always want to make sure, even if you're given the equation, that it actually is going to be balanced. Now, the second one is really important as well. Whatever they give you in the problem, you need to convert into moles. And again, you do that by what we see here and what we just talked about. That is your molar mass that you're going to do. Now, a lot of times you will be given the units in grams, and usually it's a simple sort of grams to moles conversion using the molar mass. But again, you could technically be given it in any unit. So for example, you may be given it in pounds. And if you were given something in pounds, you would have to first go from pounds to grams and then grams to moles. So I would say probably a lot of times it's just a straight kind of grams to mole conversion. But technically speaking, somebody could give you some weird units to start with. But the ultimate goal for number 2 is to get whatever units you're given, or whatever number you're given, into the units of moles. And the real reason for that is because of step number 3. You need these guys to be in moles, because when you go to step number 3, That is the big stoichiometry part. That is the part where you're going to go to the balanced equation, like we did in the previous sort of example. You're going to look at the coefficients and you're going to find the two things you're interested in. One thing you're interested in a basic stoichiometry problem is whatever they give you. The other thing that you're interested in is obviously what you are trying to find. And you want to find the mole to mole relationship from the balanced equation. So that's why in step number 2, you have to convert whatever they give you into moles so that all the units will cancel out correctly. And you would use the coefficients to do that mole to mole relationship. And then step number 4, a lot of times you do have to do step number 4. Sometimes you may not. So what it does happen after you are done with number 3. So once you finish number 3, the units you will be in are always going to be moles at that point. And that's because step number 3 is a mole to mole relationship. You will always end up in moles at that point. So if the problem wanted the answer in moles, you're pretty much done. You just slap a box around it and everything's good. If the problem wanted the answer in grams, you would have to do another conversion using the molar mass from the periodic table. And you can convert those moles to grams. And again, it may be one conversion at the end, maybe multiple conversions. So again, if you wanted something like pounds or something like that at the end of the problem as well, you would have to go from moles to grams, grams to moles. Again, could technically be asked to find any unit, but grams are usually the most common unit that you find. So these are the same 4 steps for every single basic stoichiometry problem that you would do. You want to follow the steps in the order. And if, excuse me, if something is done for you already, don't undo it. So I've seen people actually have something given to them in moles and they decide, I'm going to unconvert it back to grams and then reconvert it to moles again. So you don't want to go backwards. So again, if something is done for you, step 1, step 2, step 3, you just want to go on to the next step and you don't want to go backwards. All right, so why don't you try this one here and see what you come up with. Take a few minutes and then we'll talk about it. We got methanol, which is a CH3OH, burns an O2 to make CO2 and H2O in a combustion reaction. We want to know what is the grams when it says mass here. So we want to know what is the grams of water that's produced. And I'll give you some periodic table information that will help you. Carbon is 12.01. Hydrogen is 1.008. That's carbon. Hydrogen. Oxygen is 16 grams per mole. I think that's everybody on there. All right, so why don't you take 5 minutes or so, a few minutes, and start working on this, see what you come up with. Again, follow those 4 steps, and then we'll go over it together, make sure everybody's on the same page. All right, let's see how we did. Looks like we got an answer, so let's take a look and see. See if we agree. We might. All right, so in this in this problem here, we got a balanced equation already, which is step number 1. So that's all good. Again, if you typically see the coefficients there, probably going to be balanced, but you should also, take a moment, double check, make sure everything's good. Now, the only thing that they gave us was we have 209 grams of methanol, which is the CH3OH. And we ultimately are not interested in methanol in this case. We're interested basically in how many grams of water. So again, this is where we would use stoichiometry to go from methanol to water. We did our first step there, which is balance the equation. Step number 2 is to convert to moles. So in order to do that, we will need to go to the periodic table here and basically add up everything to get our molar mass. So 1201 for our carbon. We have 4 hydrogens at 1.008. And we have an oxygen at 16 grams per mole. And if we do all that good stuff there, we got 3204 as the molar mass of our methanol there. So 3204 grams per mole. And we're going to use that as a conversion factor to go from grams to moles. So that would be our next step. We're going to take 209 grams of CH3OH using our molar mass from the periodic table, which is 3204. That is going to allow us to convert it into moles. You don't necessarily have to get an answer at this point. You can do it all in one step, but I'm just going to get an answer for the time being. And at this point, if you did get an answer, you got 6.523. I'm just going to take it to a good number of digits there. Moles of CH3OH. So we just converted it into moles using the molar mass. Now we want to do step number 3, which is go to the equation. So again, one thing we're interested in is what they gave us, which is the methanol. And we're interested in the water as well. And from the equation, we see that for every 2 moles of methanol, we get 4 moles of water. And again, that is nothing more than our coefficients that we see there. Remember, this is really the stoichiometry part, and it really is just a conversion factor. So since we have moles of methanol on top, we want to go with the 2 moles of methanol on the bottom so that they cancel. The 4 moles of water on top. And that is going to get rid of our methanol and convert us into water. And we do end up with 13.046 if I take it out a couple digits. So now we're close to what we're looking for, except that we did not want moles, but we do want grams. So we will have to do that last step, which is to convert our moles back into grams. And again, we go to the periodic table to help us do that. And from the periodic table, we have 2 times 1.008 for our hydrogens, plus a 16 for our oxygens. And for water, that would give us a molar mass of 18.02 grams per mole. So the last step that we would do would take our moles of water. We would use the molar mass to convert from moles to grams. Moles are going to cancel. And I believe we will end up with something like 235 grams of water would be produced in that particular case. So hopefully you can see that all these are the same exact steps. This is step number 1, the balancing the equation. This is step number 2, which is convert to moles. This is step number 3, which is really the stoichiometry part. And this would be step number 4, which would be converted into other units besides moles. Again, you don't have to get an answer at each step. You could do it all in one sort of calculation. You should hopefully get the same answer there. We went with 3 significant figures because our only number in this problem is 209, which is 3 significant figures. This number where we calculate how much product we would make is what is sometimes referred to as the theoretical yield. And whenever you sort of figure out how much product you did, that is what is usually known as your theoretical yield when you calculate it from the balance equation. Let me just take a look at your question. Okay, so for step number 3, which is the stoichiometry part, it does come straight from the balance equation. So when we looked at the balance equation, the only piece of information we were given was the methanol, which is this guy, which his coefficient is 2. So what that means is there are 2 moles of methanol for every 4 moles of water, which was the other thing we're interested in. And basically, you could get inequality just straight from the coefficients from the balance equation. And technically speaking, because this is an equality, you could write 2 conversion factors. I just didn't write them out. You could write that there are 2 moles of CH3OH over 4 moles of water. Or you could write, so I'm right now, I'll go the left-hand side, the opposite conversion factor, 4 moles of water, which I think is the one we used, over 2 moles of CH3OH. So from any sort of stoichiometry relationship, mole to mole relationship that you get from the balanced equation, which again is just straight the coefficients, you technically could write 2 conversion factors for them. And that's why I say really what stoichiometry is just a conversion problem. And it's just a different place of where you get your conversion from, instead of looking up in a table like, hey, there's 12 inches in a foot, or there's 2.54 centimeters in an inch. You get the actual conversion factor from the balance equation. Other questions? So we did a couple examples, first one and this one, and these are really sort of basic stoichiometry type problems. And also just so everybody again understands that, when you have an equation, say we'll just look at this one again here. In this particular problem, we started over here and we went across the arrow to the other side. You can do that. You could also start, if you're just given information about somebody on the right-hand side, you could go back over to either one on the left-hand side. And you don't even have to necessarily go across the arrow. You could do a basic stoichiometry problem by just staying on the same side, either the reactant side, or if you had 2 products like here, you could do these same sort of 4 steps and stay on either side of the arrow. So sometimes people think you always have to kind of go left to right across the arrow when you're doing stoichiometry, and you don't. So that's really why it's sort of useful, because it doesn't really matter where you have that piece of information from. If you have one reactant, that is enough information to figure out, say in this problem, how much other reactant you would put in there, how much of each of the products you could produce, or if in this case, how much one of the products that are produced, You could also figure out how much of the other product would be produced, how much of the starting amounts of each of those guys would also be produced. Any questions on sort of basic stoichiometry problems? Again, we want to follow those same 4 steps. Okay. So I tell you, why don't we just try one more with, we'll use the same equation. Let's just say that we, just to make sure, so we won't do the same problem, obviously. Let's say that we, let's say that we started with 125 grams of O2. How much methanol would we need? In grams. So why don't you take a moment and calculate that just to make sure. Again, same information from last time. Probably could use the molar masses you got going on from last time. All right, take a minute or two, see what you come up with. I will as well, since I just made it up. Okay, so let's take a look and kind of see how we're doing. So again, we want to do the same basic steps. So obviously, step number 1 was already done for us, which is the equation is balanced. Step number 2 is take whatever they gave us and convert it into moles, which obviously in this case we need to do because we have it in grams. So the second step here would be 125 grams of O2. Again, it is the periodic table that's going to allow us to convert that, and that is 32 grams per mole, as each oxygen is 16. So 16 times 2 gives us 32 grams per mole. We're going to divide it by 32 grams per mole of O2. That is going to cancel our grams of O2. And if we do get an answer here, and again, you don't necessarily have to, probably shouldn't do that. There we go. We'll go with 33.906 moles of O2. Now what we want to do is see a couple of answers. Let's see how we did. So we have moles of O2. And again, in this case, we're not interested in O2. We're actually interested in CH3OH. So that is going to be for every 2 moles of CH3OH, we do get 3 moles of O2. Again, we could use that as a conversion factor here. We want to get rid of the O2, so that's going to go on the bottom. So that's going to give us 3 moles of O2 on the bottom and 2 moles of CH3OH on top. That comes again from the balance equation. That really is the stoichiometry part. Times it by 2, dividing it by 3 gets us 2.604 moles of CH3OH. Again, close to what we're looking for, but we do want grams in this case. So the last step, which is that 4th step that we need to do, is we're going to end up here taking the molar mass. And since we calculated on the last problem, we know that it is 32, what did I have there? 3204, I think. Yeah, 3204 grams per mole of CH3OH. And now the big reveal. I see a lot of numbers popping through there. Let's see how everybody did. 3204. I'm going to go with 84 point. I'm going to actually write it right. Yeah. It's building suspense, really. That's what it's doing there. I'm going to try that again. There you go. Helps if you read the calculator right, I suppose. Let's try that again. It is 83.4 grams of methanol. It looks like we did pretty good there on most of you. Again, significant figure-wise, when we're looking at the sig figs, we're looking at the only number in this case was the 125, which would be 3 significant figures. Pretty much everything in the middle of that calculation, pretty much conversion factors, which means the answer probably should have 3 significant figures when it's all said and done. Any question on those steps? Again, you should hopefully be able to see same 4 steps. Step 1 up there, step 2, convert to moles, step 3, stoichiometry, mole-to-mole relationship, and step 4 in this case we did need to do, which is convert it from moles to grams. Again, like I said, you don't necessarily have to get an answer in between like I did. You could do it all in one calculation, which is perfectly fine as well. If you do get an answer in between, just like normal, try not to round too much along the way. Otherwise, you may find yourself kind of far away from sort of the correct answer. Any questions on stoichiometry? So again, this demonstrates that, again, you don't have to go across the arrow. In this case, we actually just stayed on the left-hand side of the arrow. We pretty much did the exact same 4 steps, and we end up with the same sort of relationship that you could do. Any questions on that there? Yeah. All right, so these are basic stoichiometry problems. The next thing we're going to talk about are a little bit more complicated stoichiometry problems, and these are ones that are referred to as limiting reagent type problems. And the original problem is over there. There we go. There we go. All right, so let's take a look at this idea here. So typically when we do a reaction, there always is, for example, one reactant that sort of gets used up first. And that is basically what is known as the limiting reagent. And that is the reactant that gets used up first. While the other reactant is what is known as the excess reagent, which means you have plenty of it. And it's actually left over when it's all said and done. So when the reaction is actually over, you actually still have some of those reagent still actually left over. So in sort of the example on the right, the O2 is the two red circles. The NO is the red and blue circle. And we're going to make NO2, which is two reds and one blue. And you can see that as we transition from top to bottom here, all of the NO, which is the red and blue circles together, are gone. But we still have some of the O2 guys left, which is our excess reagent. And you can even, as you see here, figure out how much excess reagent you have left over. So in this little example here, we would have 3 molecules or 3 moles of the O2 left over when the reaction is done. It's kind of like when you buy hot dogs and hot dog buns. I think you get like 8 hot dog buns, you get like 10 hot dogs. So at some point you're going to run out of buns, right? And the buns would be your obviously limiting reagent. Hot dogs would be your excess reagent. And why is this important? This is important because essentially when you do a reaction, so for example, when we do like A plus B goes to make AB, we essentially need an A and a B to make our product, right? So if we say that A in this case was our limiting reagent and B was our excess reagent, just arbitrarily choose those two. What that means is at some point, all of the A is going to get used up. And that's going to be problematic because once all that A gets used up, there is no possible way for you to make more product because you actually need an A and a B to come together. So it is always the limiting reagent that's the important one because the limiting reagent determines how much product you will make. So when we are basically in a situation where we are in a limiting reagent problem, we need to determine first which one is the limiting reagent. And then once you figure out which one's the limiting reagent, that is the one that's going to basically tell you how much product you can produce. So how do you know it is a limiting reagent problem or like a basic stoichiometry problem like the few that we just did? If you look back at those basic stoichiometry problems and the information that's given to you, you pretty much were only given information about one thing. So in a basic stoichiometry problem, if you're given information about one of the reactants or the other reactant and only one of those two guys, then it is assumed that whatever piece of information they gave you, that guy is the limiting reagent and the other one's the excess reagent. So when you know you need to do this problem like a limiting reagent problem is when they give you enough information to calculate the number of moles of each reactant. So that is your kind of red flag, like, hey, I should do a limiting reagent problem. Yeah. So whenever you're given the starting amounts of both reactants, all 62 reactants, no, most of the time it'll just be 2 usually. Could be more than 2, but usually it's just 2. But if you're given enough information about both reactants, and enough information means you have enough information to calculate the moles of each of those reactants, then it is a limiting reagent problem. A lot of the steps are kind of similar to do it, but you do need to figure out that limiting reagent. Now, the way I'm going to show you how to do limiting reagent problems might be a little bit different than how you learned them before. And I'm going to kind of tell you why it's sort of beneficial to maybe do it this way. You don't necessarily have to do it this way. I will maybe show you or tell you how other ways you could do it. If you learned how to do limiting reagent problems earlier, and whatever that class is called that we take before this one, and you like doing it that way, you're more than welcome to continue to do it that way. Or if you like the way maybe it shows you in the book, which may be different as well, you could do it that way as well. Again, I don't personally have a preference, but the way I'm going to show you is sort of beneficial in this sense because it will allow you to basically figure out all the possible questions that are sometimes asked in these problems in a relatively sort of quick and convenient way, rather than maybe having to go back and start from the beginning and do a bunch of separate sort of calculations. So let's talk about a problem, and let's take a look at a problem here. And I'm going to walk you through this way of doing it. And if you like it, you obviously could do it this way. If you're not very fond of it, again, I do not have a preference, so you could do it any way you'd like. All right, so let's take a look at this. In one process, we are reacting 124 grams of aluminum, and they are reacted with 601 grams of iron 3 oxide. And we want to know how much aluminum oxide is going to be produced. So we want to know how many grams are going to be produced. So the first kind of steps, no matter sort of which way you choose to do a limiting reagent problem, which by the way, there's like 3 or 4 different methods you could do these problems. The first couple of steps are pretty much the same as a basic stoichiometry problem. The first step you want to do is make sure you have an equation that is balanced, which it obviously does look like it. You then want to take whatever they give you and convert it into moles, which we do have to do in this case. But first off, how do I know this is a limiting reagent problem? We're taking 124 grams of aluminum. We're mixing it with 601 grams of iron 3 oxide. That is basically enough information for both reactants and enough information for us to figure out the moles. So that is basically your red flag to know that no matter which way you choose to do this problem, somewhere along the way, you need to determine which one is the limiting reagent. So the second step, again, is basically the same. We're going to convert each of those grams into moles. So we'll start with the aluminum. Aluminum is 2698 on the periodic table. So we're just going to take our 124 grams of aluminum. We're going to use the periodic table and the molar mass to convert it into moles. And for aluminum, that is going to get us 124 divided by 2698, 4.596, looks like. 4.596 moles of aluminum. We also want to do the same thing with our iron 3 oxide. So we're going to take 601 grams of Fe2O3. Again, from the periodic table, we're going to add up all the parts there. So iron is 5585 and oxygen is 16. So 5585 for the iron times 2 plus 3 times 16 for the oxygen. That gives us 159.7. Again, from the periodic table is where that number came from. And if we take 601 divided by 159.7, we get 3.763 moles of iron 3 oxide. So the first couple of steps, pretty much similar to basic stoichiometry problem. And now before I show you sort of the method a way you could solve this, very commonly method to figure out the limiting reagent and how much product you would make is to do two separate calculations, one starting with the aluminum and one figuring out basically if I start with my 124 grams of aluminum, how many grams of aluminum oxide would I make? And then you would do a second calculation that says if you start with 601 grams of iron 3 oxide, you would do a stoichiometry problem to figure out how many grams of aluminum oxide you would produce. The one that is the smallest number of grams is both your limiting reagent and also your product or your theoretical yield. So that's one very common method to sort of figure out limiting reagents, which is perfectly fine and works really well. Except that sometimes when you're asked other things, which we'll talk about in just a second, you then have to kind of go back and do a number of other calculations as well. So the way I'm going to show you to do limiting reagent problems is a method which is referred to as a ICE table. And ICE table means initial, change, and for this, we'll call it end. ICE tables are nice also because if you plan on taking 200B, you do ICE tables all day long, every calculation. So it's very similar to something that calculation-wise that you'll have to do if you continue to take chemistry at 200B. So you may like this approach. And again, I'll show you maybe some of the benefits here as we go through it. Now, when you do an ICE table, you do have to make sure everybody's in moles when we do it. So that's why, again, we still have to do step number 2 here before we begin. We have to convert everybody into moles. So to do an ICE table, we essentially will take the equation, which is 2 aluminum plus our iron 3 oxide, gives us our aluminum oxide plus our couple of irons. So initially, we have the moles of aluminum, which we calculated above. So that's 4.596 moles. We also have the moles of the iron 3 oxide that we calculated above, which is 3.763 moles. And now for our product side, we are assuming that this reaction is heading in this direction, which means we have not produced any of these guys initially. So it is safe to start with an initial moles for each of those guys as 0. Now, because we are making this assumption that the reaction is heading from reactants to products, what that means is on the reactant side, that concentration or moles should be decreasing. And we represent that with minuses on the reactant side. Well, on the product side, it means we should be making more product since the reaction is heading in that direction. And we represent that with a plus. What we represent with a minus or plus when you do an ICE table is a variable, and that variable is x usually. So we use x as sort of a variable to indicate that. So when we come to the change part of the table, we're going to do minus 2x. So you may be asking, where did the 2 come from? The 2 came from the coefficient. So if you remember, when we're doing stoichiometry, these are the mole-to-mole relationship. So when you do your change part of the table, you have to take the coefficient into account because essentially what that coefficient does for you is the mole-to-mole relationship. So it does that mole-to-mole relationship that you don't have to necessarily do. When we come to the next one, which is a reactant, it's going to be minus x. Again, minus x because the coefficient here is 1. Now, when we go to the product side, we're going to plus x here. Plus x again because the coefficient here is 1. And this is going to be plus 2x again because the coefficient here is 2. Yeah? So that's really important when you do the x part of it. It not only gives you sort of the change that's occurring, but it also, you need to take into account those coefficients, because that's going to basically do the mole to mole relationship. It's going to make sure that you have the correct sort of stoichiometry involved. Any questions on that so far? So what we're going to do now is essentially just bring everything down to our end. So when we bring everything down here, we will end up with 4.596 minus 2x. This is going to be 3.763 minus x. This is going to be x, and this is going to be 2x. Yeah? And remember that the x in this case really represents the moles of change, right? So the x represents moles. That's why these are in moles, so everything cancels out correctly. All right, so any questions first off on the table here? Now, because it is a limiting reagent problem, we do need to figure out which one is the limiting reagent. And to do that, we're going to do two very quick and simple calculations, and they are based off of our products. I'm sorry, reactants. What we're going to do is set each of these guys individually equal to 0. And when I set that equal to 0, that essentially gives me 2x equals 4.596. And that gives me an x value that is equal to 2.298 moles. 2.298 moles. We will also set this one equal to 0. 3.763 minus x equals 0. And pretty much x equals 3.763 moles. Now, what these two little calculations are doing for us is it's going to allow us to figure out which one's the limiting reagent. The limiting reagent will be the smallest number. And in this case, that is this number right here is our limiting reagent. So what that means is the aluminum in this reaction is our limiting reagent. By default, the other guy would be our excess reagent, the iron 3 oxide. So that X is really important, and that means that we technically don't need this number anymore. And why this table method is kind of a nice method is for what we're going to do pretty much right now. And that is we're going to basically solve for everybody here. So when we get that x value, that is the x that we would want to use here. That's also the x we would want to use here. That's the x we would use here. And that is also the x that technically would be used there as well. So we'll start first off with the question it was asking, which was how many grams of aluminum oxide did we produce? 203. So what we could see from the table is that the moles of aluminum oxide equals X, and we see that X is 2.298 moles of aluminum oxide. Then we could use the molar mass of aluminum oxide from the periodic table to convert that into grams. And if we do that from the periodic table, aluminum, which is 2698 times 2 plus 3 times 16 is 101. We'll call it 102, it looks like, maybe. So try that one more time just to make sure I punched it in right there. 2 times 26.98. So we'll call it 102 grams per mole. And that means that we would produce, in this case, about 234 grams of aluminum oxide. This would be our theoretical yield for aluminum oxide. Any questions on that so far? So here's sort of where the benefit of this table is. A very common question that you're asked for is, for example, how much of your excess reagent is left over? And we could do that calculation relatively quickly as well, because what we know is if we look at our excess reagent over here, when we get to the end, it equals 3.763 minus X. So how much of our iron 3 oxide left over? We then could use our table to help us answer that really quickly without having to go back and calculate some other things. It equals that. So that's going to give us 3.763 minus our X value, which is our 2.298. And that gets us 3.763 minus 2.298. 1465 moles. And again, we could use the molar mass there from the periodic table, and we actually have it above because we used it to calculate to start with. So from above where we used it before, which is right here, it's 159.7 grams per mole. And again, a very common question, like I said, is to figure out how much of your excess reagent remains. And in this case, we actually have the same number, 234 grams of our iron 3 oxide is left over. So you can see relatively quickly, because we sort of did this ice table, we could answer that very common question of not only how much did we produce, but how much of that excess reagent's over. We could also, if we wanted to, very quickly figure out how much of the other product we would produce, because what we know is iron at the end is equal to 2 times X, which means 2 times our 2.298 gives us 4.596 moles of iron. And so run out a little bit of room, we'll times it by the molar mass, which is 5585 grams per mole. And we would end up with times 55.85, 257 grams of iron would also be produced in this case. Also would be the theoretical yield of iron. So you can see relatively quickly by doing sort of this ice table approach, you can very quickly with minimal calculations figure out pretty much everything that you would want to know. Obviously, since our aluminum is our limiting reagent, if we put our X value back into here, we probably should end up pretty close to 0, which is what we would expect, as it would be all completely used up. Any questions on that step? So again, in this particular problem, it actually only asks for this. But again, you can see relatively quickly, you pretty much can answer every other thing that would ever be asked of you in a very quick sort of fashion. Any questions on an ice table approach to doing limiting reagents? All right, like I said, there is multiple ways you could do limiting reagent problems. And if you've learned a way in the past and you're like happy with it, I'm okay with it. You do not have to do an ice table, but it is something that will allow you to answer questions really quickly. It will also be very helpful if you kind of get a hang on it, if you're planning on taking 200B, because pretty much a majority of all the calculations you do are very similar to these. and it'll sort of help you out in that aspect of it. Now, I think I have on here sort of an alternative way of solving this problem. And again, I'm just going to scroll through it so you'll be able to see it. And again, if you're reviewing this later, you could slow it down and kind of look at the steps, which would be another approach to do this. So here again is a different approach where we're not going to do an ice table for the same problem, just to kind of walk you through the steps. Again, it starts out very similar to what we talked about. So we figured out in this particular case, what they did is they took 124 grams of aluminum, they converted it into moles. And then what they essentially figured out was how many grams of iron 3 oxide they would need to use up all of the aluminum. And what they figured out was they needed 367 grams of iron 3 oxide. They started with 601 grams of iron 3 oxide. What that tells you is the iron 3 oxide is the excess reagent because they had enough, and that by default, the aluminum would be the limiting reagent. So this is, again, more of a third way of doing this problem, where you take one of the reactants and you figure out how much of the other reactant you need to use it up, and you can determine which one is the limiting. At this point, what they will then do is start with the aluminum because it's the limiting reagent, and they will then figure out how much product they would produce, which is what this calculation is showing you. And as you can see, they ended up with the exact same answer as we got from the ice table. Now, this again is another approach to doing limiting reagents, where you choose one of your reactants, you do a stoichiometry problem to figure out, do you have enough to use up the other reactant, and determine which one's the limiting reagent, and then just do a stoichiometry problem, obviously using the limiting reagent. Downside to this problem is not necessarily anything other than if you were asked something like how much of that excess reagent is left over, or how much of the iron you would produce, you may have to go back and do a few other sort of calculations that might take a little bit longer to figure it out. All right. Any questions on those steps? So whenever we do calculate something from the actual equation and we calculate how much product that we produce, that is what is known as the theoretical yield. And the theoretical yield is the maximum amount of product that you should get in a reaction if everything went perfect. So starting with your limiting reagent and the balanced equation, if everything went perfect, you didn't spill anything, you didn't drop anything, you weren't a klutz, there wasn't any side reactions or anything going on there, this is how much you should yield. It's really your maximum yield, and it's always calculated from the balanced equation and what you're starting with. The actual yield is pretty much what it sounds like. It is actually how much you get when you do that reaction. So it's actually how much you produce when you actually do that reaction. In a textbook type problem or those type of problems, that is usually given to you. So the actual yield is usually provided to you in the question. You usually will have to calculate the theoretical yield. And to calculate the theoretical yield, it may be a basic stoichiometry problem to do that, or it may be a limiting reagent problem to do that, but usually you have to calculate the theoretical yield. And when we put both of those things together, we get the third type of yield, which is the percent yield. The percent yield is the actual divided by the theoretical times 100%. And the percent yield is basically what we use to determine, how good or bad we did a particular reaction. Typically, your percent yield, you want near 100%. That's good. So a high percent yield is good. If you had a low percent yield, it means you screwed up somewhere probably. Not so good. So if you had like a 5% yield, that was not so great. You probably spilled everything along the way. or threw something out along the way. But we take the actual divided by the theoretical times 100. It is possible to get a percent yield above 100. So it is possible to get that percent yield over 100%. And that also means that you probably screwed up. That's not good either. Yeah. So if you found yourself with 150% yield, you can't just go, well, I think I did 50% better than everybody else. It means you did like 50% worse than everybody else, I think. When you get over 100%, that usually means that you did something not so right. And that will very commonly occur when, for example, if you made a precipitate and you did a precipitation reaction and you're trying to figure out how much precipitate you made, a lot of times in that process, you'll take a funnel, or a badly drawn funnel there, and you'll basically put some filter paper in there. You'll pour your liquid with your solid through it. You'll collect your solid on a piece of filter paper. And obviously there would be liquid that would go through. And since there's liquid that would go through, this filter paper here is wet. Yeah. So sometimes when people do an experiment like this, for example, and they don't let the filter paper completely dry, when they go to reweigh it, they're going to have a greater mass than they should, because they will be counting the mass of the water that's still there because it didn't completely dry as basically the product. And that's usually when you find yourself with a higher than 100% yield. And again, you get the unhappy face. Not a great deal in that case. Any questions on that? All right, so I think we're getting to the end here. So I think we will stop at this point. We'll do a couple more examples, obviously, of percent yield and limiting reagents. The actual yield in a textbook problem would come in the actual problem. So in the problem, they'll say, for example, here's the next example, which is a sort of percent yield type question. So, for example, if we look at this next one, we'll do the calculations and stuff next time, but because it'll take a little too long probably to start it now. But if you look in this problem and it says something like calculate the theoretical yield, and then it wants you to calculate the percent yield if you produced 5.42 times 10 to the 6 grams of TI. So usually in the actual problem, when you're doing a textbook problem, they will actually give you the actual yield. And it's usually the theoretical yield that you actually have to calculate, like we've been doing in the last several problems, doing a stoichiometry, either a limiting reagent problem or just a basic stoichiometry problem to calculate the theoretical yield. In the laboratory, if you were actually in the laboratory, your actual yield would be actually, for example, if you did that reaction where you got a solid, how much precipitate you made would be your actual yield when you would do that particular reaction. So in the laboratory, you would actually sort of experimentally determine your actual yield. But in a textbook problem, usually it's given to you somewhere in that actual problem. Other questions on that? Okay, so a couple of things. So we've gotten into stoichiometry. We did stoichiometry. We did limiting reagents. We talked about percent yield. That also means that the study assignment that is technically scheduled for today, you should be able to at least start it as well. So again, a couple of the study assignment F, I believe, and experiment 9 is due next week. I think study assignment E is due tomorrow. So make sure that you get that one done. That again is the net ionic equation one, study assignment E. Study assignment F and experiment 9 is the redox stuff, which will be due next week. And you should, at some point when you get a chance, start working on the study assignment that's technically on the schedule for today. I think that study assignment, I'd say alphabet, right? So that's E, F, G. So that should be perhaps study assignment G, if I'm not mistaken. And that is a stoichiometry. So based on what we talked about today, you should be able to do most of the calculations on there. There are going to be some that involve solution stoichiometry, which we'll get to in the next lecture. So obviously you can't complete it at this point, but you probably could get a good jump on it to keep pace and everything like that. Any questions on any of that stuff there? Okay. So we'll take a break here. I will open up the lab if you do have questions on, again, I guess at this point it would be experiment 9. It would be study assignment F. I guess still, if you have questions on study assignment E, I can help you out with that. And again, if you have some questions on stoichiometry or something like that, I'd be happy to help you out with any questions that you may have. And again, it won't be due probably next week, but it'll be due towards at least maybe the end of next week or the beginning of the following week. So again, you might want to get a jump on that one as well. So any questions on any of that? I do apologize. It's been a very busy week. I've had, I think, 3 exams and some quizzes and that type of stuff. So I have not yet fully completed grading your exams from last week. So my goal is to hopefully get them done sometime this weekend, definitely before Tuesday. And at some point, they will be the grades will be uploaded, and you'll be able to see them. When they are graded, you will be able to go back and you should be able to look at the exam that you submitted and the actual exam, and you should be able to look at the work that you submitted and see what was sort of marked wrong and stuff like that. So I apologize. I just haven't got through them all yet. It's a little bit difficult as well. You got to do it on the computer and stuff like that. So my goal is to hopefully get them done over the weekend, and at some point very soon, I'll get those up there so you can see how you did. Any questions on anything else? Okay, so if you have questions, like I said, we'll start at maybe about 7:15ish or so, and I'll hang out for a bit. If you have questions, feel free to come by and ask. If you're out, then have a good rest of your weekend and all that good stuff. And I will see everybody back live on Tuesday after today's lab, obviously. Have a good rest of your night, and I'll see you in a bit if you're coming to the lab to ask some questions about any of that stuff.